of this communication. All right, I will continue working on the high-speed flighter. I think maybe next week's lab, you have to design a high-speed flighter from scratch, and including the stick diagrams and layout as well. And we'll have a quiz in the last 20 minutes of this class, right? On stick diagrams, I'll give you logic expressions, and you have to design the complex CMOS logic. Wait, yeah, so it's going to be a CMOS transistor level circuit and a stick diagram out of it. Okay, I'll give you 20 minutes to work on that problem. So besides that, any comments or questions or anything regarding this class? Is this fast or too slow, or it's about right? It's fine. You need more quizzes or to keep you guys on your toes? What about the workload? Okay, not too much, not too less, not too few. Okay, and we don't have like 3 to 4 exams in a semester like other classes. But we have a lot of quizzes, right? So I think you guys will be fine with quizzes. So just let me know if you have any comments. Feel free to bring it up. Okay. So that's the schematic of the ripple carrier flighter. What is this carry? What is this one? I'm just repeating, right? So you guys, after I repeat for several times, you should just let me know the answer. This is C what? C minus 1. As this is how we label it. There's nothing about minus, right? It's just like how we label it, because this is C0, this is C1, this is C2. And that's S1, is that correct? No, that's S0. S1, S2, and that's C2. And that's the final result for this flighter, and there's no sign involved. Just always treating the numbers as a positive number, but whenever you need a 2's complement, right? So these are the inputs. So that's positive numbers always. If you need a 2's complement, you need an XOR gate. That's A2, A1, A0, and that's B2, B1, B0, and this line here for the other input of the XOR gate is a control bit, right? It's a switch, and that switch is being shorted to C minus 1 directly. So that's one of the topology you need to know, and we can program it on IPGAs. If you take CE433 in the spring, it's a lot of fun, you know, to play around with this one. You can program it and directly download it into IPGA chip and make it work with LED and switches. And so that's one structure you need to know. And another one, we brought this up on Monday. AB, and that's Y, that's output, and you need a S, that's a switch, being connected to the NMOS here, and the PMOS here, and it needs to be inverted and being connected to the other pin. So this is a mux, it's a 2-to-1 mux compared to the logic compared to the one we got from the truth table, this has less number of transistors, so it's going to take less space. So we're going to design the schematic of this one and lay it out in the lab. Just keep in mind. So that's the mux. It's picking up one of the inputs and send it to the output. So here's S, and you have to invert it. So that's S bar. That's all you need for the mux. And now let's see how this works. Is this selecting one of the two inputs and send it to Y? So if S is 1, then what's going to happen? This NMOS is on, right? What about this PMOS on the top? Also on, because it's a low voltage at the gate, because it's being inverted. So this one is on. So B is being sent to Y, but we still have to look at A. Because S is 1, so 1 is being sent to the PMOS, so the PMOS is off. And also the you got a 0 for the NMOS for this transistor as well. So A is not able to pass to Y. So that's why it's only selecting B, just sending B. Whatever B is, can be 1, can be 0, to be sent to Y. Since you have two transistors, one is a PMOS, one is NMOS, and PMOS is good at passing ones, and NMOS is good at passing zeros. So can whatever S is, and whatever B is, it's a digital circuit, right? There's no intermediate values. It's going to be 1 or 0. So it's always being passed to Y. Is that correct? And if S is 0, Y equals to A. So based on this logic, we know this is a mux. So it is a mux. And you can use a mux for this circuit as well. Why do we want to use the mux instead of a XOR gate? So what is XOR? A not B or A B not. Definitely you can design a AOI logic from it or a complex CMOS circuit. But how many transistors you need from that circuit though? This is only 4, right? 1, 2, 3, 4. One inverter as well, but inverter is pretty simple. So XOR seems like just one logic operation, but it actually involves a lot of gates in there, and which will introduce a lot of time delay. So if you have this transmission gate and the mux, and you can replace the XOR gates with the mux circuits. And how that works? Let's draw the schematic on the next page. So now we're using mux and I phase. That's C minus 1, C0, C1, C2. These are the S, S0, S1, S2. Still A2, A1, A0. So these are the addends, right? And then B, you need a mux this time instead of a XOR gate. And now let's see how that works. That's a mux. And that is B2, B1, B0. So this is the output of the mux. Output. How many inputs do you have for the 2-to-1 mux? How many inputs? 3, including a selection bit, right? So the mux, that's one input. And if we invert it and use it as another input, and we can select if you need the original B or the inverted B to be sent to the output. And how to do that? Do you want to short these 3 pins together? Do you need a one selection pin or do you need the multiple ones? Just one. So let's see. These are the two inputs, right? So the original B or the inverted B. And you can consider them as A and B for the two inputs to the mux. And to do a subtraction, what's the data do you need, or what's the voltage do you need for this control line? So for example, that's the first option, that's the second option. First, second, first, second. So you need a 0 to select this bit, and you need a 1 to select this one. See here? It's always when you have a 0, when S is 0, it's selecting A, selecting the one on the top. When S is 1, it's selecting B at the bottom. So it doesn't have to be B, it's just the name of it. It's just selecting the data, whatever data at the bottom. So for this one, the same thing. Whenever the selection bit is 0, it's selecting the original B. Whenever the selection bit is 1, it's selecting the inverted B. So now the purpose right now is to do a subtractor. It's 2's complement. So whenever you have a negative number, whenever this guy is adding to a negative number, it's actually making a subtraction. So in that case, you need to invert that data and plus 1 to make a 2's complement, to get a negative number of it, right? That's the purpose. And now we are using a mux to implement that function. So if I need a subtraction, what's the bit do I need for this control line? So these are switch, right? So do you want to just switch it to 1 or to 0? Huh? Yes. So 1 is subtract, right? And why? Because 1 is going to select the inverted one. What else do you need for this circuit? The carry. Whenever it's 1, you invert it and then plus 1, so you can get it done. I think this is the same circuit on the lab, on the lab web page, right? In the report, in the instruction. Okay, and these are still 1-bit full adders, right? Are they? Yeah, so these are 1-bit full adders. So definitely remember the full adders logic. S equals to A, XOR B, XOR CI, and CO, the final CO here, is A or B, CI or AB. So there are a lot of gates. Not mention this one, but also, you know, the XOR gates have a lot of gates in there. It's a lot of time delay, can make the operation pretty slow. So I want to design a high-speed full adder out of it using the complex CMOS logic. And remember, the starting point is you still have to convert the logic expressions to something underneath the bar, right? Remember? It's going to be on the quiz as well. So you convert this one to the like parallel PMOSes, serial PMOSes on the top and at the bottom, things like that. And then draw stick diagrams out of it. So let's start from here. So that's a logic expression for the full adder. You don't have another option. That's it, because that's gonna do the job for you to get you a full adder. So we are not going to change this one, but we are going to just trying to convert it into a form that we can directly use it for something like this, and then convert into the complex CMOS, right? Complex CMOS logic. So first, starting from this one, so S equals to A XOR B XOR CI, which is A not B or A B not, and XOR CI. And this is the entire thing not, right? A not B or A B not CI, or A not B or A B not CI not. That's how you expand it. It turns out to be this. Yeah, let's run through it, see what's going to happen. And now split the bar, change the sign. You're getting A not B not and A B not like this, and a CI, or A not B CI not, or A B not CI not. I'm pretty sure we can simplify this part. So it's getting you A or B not, A not B. And then expand it again, you're getting A. So this one, A not is 0, B not 0, so only have A not B not left, CI, or no, A not B not, and AB. Right? So this is this, and we don't want to directly use it because these are just too many of them. There are too many gates, right? So there's a way to simplify it a little bit. So let's look at the CO first before we move forward. I'm not going to ask you to derive it, I think, in the quiz or exams. If you are being asked to derive it, it's going to be like in a lab, just show it on the paper, and I'm already doing this for you here. So I couldn't remember that. It's not making sense to memorize it. So what is CO? A or B, CI or AB. So the point here is to make CO part of here, because we have to do CO anyway. So after, imagine that, because this is not difficult. So we can directly get a circuit to get a CO out of it first. And if this one contains a CO, we don't know yet, but we are going to convert it into something CO. And we can directly use CO in here. So we don't have to make another circuit. That's a concept behind the scene. So the task right now is how can we convert this guy to make it into something CO? Because you have to do this anyway, right? It's not difficult. And you have to design a circuit to do this. So I think the equation looks like, so let's get the CO not first. A or B, CI or AB, right? A CO not is something underneath the bar, so we can directly convert it to the AOI logic. And next, split the bar change the sign, A or B, CI, or AB, not. Do I have to do it again? Yeah, do it again. Then A or B, not, or CI, not, and A, not, or B, not. And you got A, B, or C, not. And then expand it. You're getting A not, B not, or A not, C not, or still A not, B not, so you can cancel it, and B not, C not, right? So I think I stopped at here. So I think we are fine to just stop here for now. And so I made up one thing here for A or B or CI. So this one and CO naught. I will find this useful pretty soon. So A or B or CI and C naught. Here's C naught, right? And then we expand it. It's A or B or CI and A naught, B naught, or C. So CI, sorry for that. This one, A naught, B naught, or CI naught. And A naught or B naught. And then this equals to, God, it's a lot of work. So what I did is I combined these two because A and A naught can be canceled out, right? So 0 in the OR gate, so it's just nothing. So it's going to be this, and A and B naught, and then A naught B, and A naught CI, and B naught CI. That's the final result. Let me see if this is correct. So this one, so that's these two combined. And you still need to AND A naught, B naught, or CI naught. And this one can be simplified to what? Not really, have to expand it. My goodness. All right, the good news is like you got A naught, and A, B naught and B, things like that, so you can cancel them out. For example, if you expand this one, you get this and this is a 0, so just cancel. And this, you have to write it down here. And then this and this canceled. And this has to be written down here. And this still there. And this canceled. And this is still there, right? And this is canceled. So we have four terms left eventually. So the reason I want to do that is if you compare this one to the one we had for S, they are very similar. So that's the main goal here. So what is this? This is this term, and S is here. So you can see there are Very similar. So what are the common terms in between these two? A naught, B naught, Ci, A naught, B naught, Ci, A naught, B, Ci naught, A naught, B, Ci naught, A, B naught, Ci naught. They're all the same, right? So that's for, is there anyone we can cancel? Are they the same? Yeah. So S turns out to be this one, or see, so this 1, 2, 3, these three terms is exactly this. So I just write it down here. But you need one extra term to finish the logic for S. It's not too bad, since compared to the original one here, it's still simplified a lot. The reason we have to do this is because CO is being used, and we have to do CO anyway, and we can directly use CO here, and CO is part of that. CO is part of S. Definitely not a unique solution for it. It works. Yeah, spend some time on it to can make the circuit easier. And so next, we have to find out the CMOS level circuit, right? Let's see how we can draw it. So let's start with CO first. We can directly use this and invert it, right? So this is CO naught. If you get this done, then you can just invert it later. So you don't have to do all this De Morgan's law and convert, right? It's not too bad. If you got a little inverter, it's a trailing inverter, right? Just following. So should we, what's the circuit look like if you have this one, this kind of thing? A, B, C, I, three signals, right? And so in series. And let me see, should I do AB first or these first? So I did AB first. So AB is a non-gate here. So you are going to have A and B in parallel. And series with everything here. So AB again in series and CI. Right? So that's A, B, CI. So that's for the PMOS. For NMOS, AB are in series. And then A or B, CI, so what's the result here? CO naught, right? So we need this. We got CO. And then look at this one as S. For the full adder, you just need a CO and S. So now CO is already done. And you can directly use signal, right, to your S. So now you have how many signals? 5 signals. Oh, 4 signals. for the S. 1, 2, 3, 4. So for the circuit, it should be where do you want to get started? Like ABCI, need a A, B, CI in parallel on the top, and in series with all these things. So ABCI here first, and then CO naught. So which is actually this guy. That's for the top part. And now let's do the NMOS. So that's ABCI, ABC. So that's this one, right? So this is this one. And that's this one. And this one is here. First, these are in series. And then these are in parallel with this one in series. You can draw either one on the top. So I did this one on the top. And then 1, 2, 3. So that's CO naught. It's A, B, CI. That's everything about the CMOS level circuit. Then we'll work on the stick diagram on Monday. So be ready for the Tuesday's lab. All right? Any questions on this? No?